Hi everyone. So today we're going to talk a little bit about position, time, displacement, and velocity, and a couple other things. So this here is in our unit of kinematics. So kind of the goal today is to define these terms, understand them, and how to calculate these quantities and use them precisely, because it's very important for us to be able to be eloquent in physics. So meaning that we're able to precisely state and correctly state exactly what we mean. So we have to use precise terms to do that. So first you might ask, what is kinematics? Right? Or this unit is kinematics, what is it? Well, it comes from the origin, is what I'm interested in here. It comes from the Greek word to move, kinin, I don't know how to pronounce it, but it means to move. So basically this is going to be the study of motion. So we'll be studying motion pretty much throughout our year this year. This is basically what kinematics means. So I kind of want to start things off with something that's ridiculously important. There really isn't a better place to put it than one of the first things we learn in school year, and this is a frame of reference. So what a frame of reference is a point of view. That's the way I like to describe it. So all measurements are made relative to a certain point of view. And so what I kind of mean by that is that we can have different frames of reference. So for example, if we're sitting on a train, and let's say it's moving at 80 kilometers per hour to the right here, and you're sitting on this train and a person walks past you at a speed of 5 kilometers per hour. Okay? I say this speed of 5 kilometers per hour in the reference frame of the train, or your reference frame. They're one and the same here because they're moving at the same speed. This is important because we could also describe this person's motion, their speed, as if we were standing outside of the train. Right? Outside the train, we see the train moving at 80 kilometers per hour, but that person's also moving a little bit faster than that, 5 kilometers per hour faster than that. So the person standing outside the train, we see them moving at 85 kilometers per hour. Right? Kind of the same thing if the person was moving in the other direction. From outside the train, they actually look like they're moving at 75 kilometers per hour, whereas we would still see them moving at that same speed of 5 kilometers per hour sitting in the train, but in the opposite direction. So moving on here, kind of talking about position and coordinate systems. So just kind of first things first, when I talk about one-dimensional motion, it's basically just an object moving along a straight line path. Right, so if we're to draw, let's say drawing a motion diagram of their motion, we'd be able to take a ruler and draw a straight line through their dot diagrams. So this is one-dimensional motion. What's also going to be useful is for us to state a position. So a position is a way to state the location of an object at a certain moment in time. A lot of times, the time element's going to be implicit, but position helps us say where they are. And the thing with positions, we're going to have to say their position in reference to an origin. A lot of times we'll be basically marking our origin as what we're calling our 0 point. Origin is arbitrary. It doesn't matter where you call the origin. Sometimes it's going to be more convenient to call certain locations our origin with respect to others. Now, using this combination of an origin and an axes, base and referring to a certain direction along these axes as positive and the opposite direction as negative, makes a coordinate system. So we'll be using coordinate systems very often in this class. Our first couple lessons here we'll be dealing with just a one-dimensional coordinate system, so just a line with tick marks or something along that sort. Whereas we'll be moving on to perhaps two-dimensional coordinate systems. And sometimes three-dimensional coordinate systems are useful, though we won't really delve into that too much in this class. So kind of an example of a one-dimensional coordinate system here is this diagram here. So we have a post office here at the center, and I decided to label this as my 0, or the origin, just because in describing the location of this cow and this car, it's going to be easiest to refer to the post office. So here I could describe the location of the car as either being 4 miles to the right of the post office. Maybe this is the eastward direction, something along those lines. Though if I call the positive direction here to the right, then I can just say that the car is at position 4 miles, a positive 4 miles. Whereas the cow, on the other hand, since it's to the left of my origin, to the negative side of my origin, the cow is at a location, you can either say 5 miles left of the origin or a negative 5 miles. So here, this positive and negative signs indicate direction, and that's super important. We're going to be doing that a lot. A lot of times it's going to be simpler to indicate direction with this positive and negative sign. May not always be the case. Since we're dealing with one-dimensional motion, we can. Later on, when we deal with two-dimensional motion, we are going to have to actually use angles to help us indicate direction. But we're not going to worry about that now. Here, positive and negative signs are useful. The reason why we use positive and negative signs really is because, long story short, physics people are lazy. You and I are lazy. So we want to write the least amount of words or numbers as possible. So when we're dealing with the location of, let's say, this car, instead of saying 4 miles to the right of the post office, since we define the origin of the post office and the right words being positive, we can just say it's located at the location of positive 4 miles. A lot less writing to do. Now when it comes to one-dimensional motion, most often you're probably going to be comfortable with it being horizontal, like we just did with the post office. That was horizontal. But it doesn't have to be. It can be vertical. So for example here, we have a rock falling towards this person, right? So this rock is falling. If we were to make a motion diagram, it's just completely vertical. We can draw a straight line through those points. So that's also an example of one-dimensional motion. Although horizontal and vertical is going to be the most common, it can also be diagonal. So for example, here we have a person on a mountainside, and this mountainside happens to be at a constant slope. So this person here, if we were to plot their motion, we could draw a straight line through all their motion points. So it is also moving one-dimensionally. So now I'll kind of mention time. Time is very useful in describing motion. It kind of tells us how the rate of things are changing or how they're going. So for example here, if we had a dot diagram as shown here on the left, we're not really sure if this is a leisurely stop or a screeching halt. In fact, here we're not even sure if the object's moving to the right or moving to the left. That's also not indicated. So here labeling time can be really useful. So if we were plotting the time, so just remember with dot diagrams, each dot is the same time interval apart, right? So kind of looking at to the right here, if we have an object that is moving to the right, we see at time 0, it's located, I don't know if I have Screencast-O-Matic or the app I'm using here highlighting, but at time equals 0, we see that and the next moment in time is at 1 second, and then 2 seconds, and so on and so forth until 8 seconds. So we see here that an object is moving at a constant speed or constant rate up until about the 4-second mark, and then it starts slowing down. And we see here now that we've labeled the time that the object is moving to the right. We don't always have to label our first dot as being time equals 0. Just label our 0 time wherever is useful. So if we are only interested in the time period of which the car is slowing down, then just starting at that dot could be the most useful, and counting time equals 0 from that point. We won't necessarily be labeling dot diagrams with times very often, but it's just a useful tool to think about, and kind of a useful tool to describe how time is useful in physics. And moving on to probably one of the most important ideas in physics is the difference between a scalar and a vector quantity. So a scalar is just a numerical value that does not have a direction. It only has a magnitude. Right? So magnitude just means numerical value. At least that's how I like to think of it. So a scalar quantity just has a number value associated with it. It can still have units, but there's no direction. So examples of this would be time, temperature, charge, mass, moles, speed. Some of these quantities you may not be familiar with, but for example, time you can say, oh, it is 3 o'clock. Or you could say, oh, it took 5 seconds to do such an action. Right? So those are scalar quantities. There's no direction associated with it, but yet they're still units. Now, a vector quantity is a quantity that has both a numerical value and a direction. has both magnitude and direction. So examples of this that we'll be dealing with throughout this course are going to be displacement, velocity, acceleration, force, torque, momentum. And I also mentioned fields here, though we'll be dealing with that more implicitly, but it is a vector quantity. So we'll be dealing with vectors more and more often in class. We're going to get more and more comfortable with this vocabulary. So vectors have magnitude and direction. So a lot of times a problem might prompt and ask you for the magnitude of such and such quantity. So that's just saying they want the numerical value, including units, when applicable. But they don't really care about the direction. That's not necessary in their answer. So you don't need to indicate direction there. But the problem doesn't state just find the magnitude of it. It just says, find the value of displacement. That means that we have to state the value of the displacement as well as the direction of displacement. This will make more sense as we get more into things. So, talking about displacement, let's just deal with this quantity. So the symbol we use for displacement is going to be delta x. So x, what I'm referring to here is position. So when we're dealing with a position or a location, we're going to use whatever coordinate system we're dealing with, and x is just the general one we're going to use for the most part. Sometimes we might use y as our coordinate system, especially if we're dealing with two-dimensional, we'll have x and y coordinate systems. If you move on in physics, you'll also be dealing with z being the third dimension of space. But I just wanted to use the symbol x here just because that's the most common thing you'll see on the, what's the word I'm looking for? Formula sheet. Our formula sheet likes to use x most often. And the symbol delta here means change in. So we'll be using that symbol a lot. You might be familiar with it from chemistry class. So delta x means change in position. So that's literally what displacement is. It's the change in position of the object. Displacement is a vector quantity, so we want to also indicate direction. So it has magnitude and direction. So to think about displacement, so I kind of have a picture here. Displacement kind of goes hand in hand with distance, though they're not the same thing. So displacement is the straight line distance from point A to point B here. And we also have to indicate direction. So that's how we describe the displacement here. Whereas distance is however long it takes to get from point A to point B. So for example, if we have a person walking on a path and they actually take this blue dotted line that's labeled distance here, and we were to measure how long that took in terms of length, maybe that took 5 meters. The displacement of this person is the straight line distance from A to B in that certain direction. So that person's displacement is going to be smaller than the distance they actually traveled. We'll be working with a lab to help us develop this idea in class. So kind of more of a physical example, or more literal example here, a word problem. Physics, full of word problems, so we'll get used to them. So we have Ricky here, and Ricky is standing 50 feet east of the corner of 12th Street and Vine. He then walks to a second point 150 feet east of Vine. What is Ricky's displacement? So first things first we're going to do is draw a diagram. I'll talk about this note in a minute, probably in the next video, looking at the time constraints. But you're going to want to draw a diagram. Drawing a diagram is the first step we're going to take in pretty much every single problem. So here what we might have is a coordinate axis where we have Vine running north-south, 12th Street east and west, and we have some horizontal coordinate system. Here I labeled it X. I have unit of feet, and I labeled my origin as the intersection of Vine and 12th Street, just because it seems like it makes sense. So I labeled Ricky's initial location at a location of 50 feet and their final location at value of 0. So we'll continue talking about this problem in the next video.